Hello everyone. Here we are again. In tonight's video, we will talk again about the tests we do on the boards, on various boards, what we can measure on the boards, what we see on a board and what we can perceive that happens when the current circulates inside it, when we use a multimeter, an oscilloscope, other instruments. We'll talk a bit about waveforms, where can we find, and I will tell you, as simply as I can, what measurements we can take. What the multimeter and oscilloscope show us. And I want us to remember that when we repair a circuit board, we have as a rule that the manufacturer has done their job well, has studied the circuit well. So there is no need to measure, probably no need to calculate currents and voltages. These are standard. The manufacturer has calculated them for us and has given us their prices. So in a few words, when we do a repair, we don't think about types. We don't think about why this component is so similar. A solution so similar because we have put this diode for this capacitor. And in general, we don't operate as manufacturers like this. We will do a repair because they have fixed this point and others have studied it for us. Of course, we need to know how they solve various circuits, such as transformers, amplifiers, or components, transistors, resistors, and capacitors. So we need to know what will happen if current passes through them, alternating or continuous. So let's get started to see a motion picture well known to all of us. So we have all encountered it. No matter how much of a beginner someone is, they have seen it. And let's explain how we measure it and what exactly it is. So we are talking about alternating current. Let's design and see its characteristics in order to measure a waveform. First of all, we need the oscilloscope. It's an instrument that visualizes for us what the voltage does in circuits. The voltage changes in circuits. It has two axes. One is time and the other is voltage. Voltage is vertical on the vertical axis and time is horizontal. I will draw it here. I will make two axes, one horizontal and one vertical. The horizontal is voltage on the vertical. Symbolized by beta, and on the horizontal axis is time, symbolized after time is seconds. So basically we use subdivisions of the second, usually microseconds, to catch the changes. And I will explain it a little better below. So we said horizontal are the small seconds and vertical are the volts. I will use the voltage of the network that we have here in Greece, 220 volts, to show you how exactly they are represented on the oscilloscope. Then on each axis we have millivolts in the middle, the positive values towards the top, and the negative towards the bottom. We'll put in the negative values, heat down the minus 220 volts that will appear on the oscilloscope to measure our network, and in the positive values, heat up the plus 220 volts that is in our network. We get plus 220 minus 220 volts to tell us that we have 220 volts. That is in the alternating. This is understood. That's from peak to peak. In the cybernetics, we have 440 volts, 440, and we start the voltage 0, 1, 2, 3, 4, goes up to 220 volts, goes down, reaches 0, and then goes minus 1, 2, 3, down to minus 220 volts, ends at 0. This is alternating current, and this is also a waveform, as it will appear on the oscilloscope. If we measure this, it will be done, we put it in slow time. So when we see, if we put it in slow time, we will see the voltage rising from 0 to 220. It takes some time to rise up there, and then it goes down to 0 again, and goes down to minus, and goes to minus 220 volts. This is what makes the voltage in our network at 220, if it were happening above a lamp, and we could reduce the time, we see in slow motion, we will see that the lamp lights up, goes out, and lights up again. This will do continuously, but because it does it very quickly, I don't see it with the human eye, and I see that the lamp remains continuously lit, let's say. Now what? It is the period, so a complete change of the current one, a complete cycle that is from plus 220 to minus 220, back to zero is the period. That is the time from here, so that it starts from the middle volt and up to here where it makes a complete change. This time is the period. So the period is here. Time is period is symbolized with capital T and symbolizes the time that makes a complete oscillation. The voltage is in the previous period, because from here and below we said it continues. So here the voltage continues and goes up and down, but it's the same thing. It's the same thing. We say it does the same thing again, 0220, 0220. The minimum time it takes for a complete oscillation is the period like this. And that is the period is here, and the frequency we are talking about now, the 50 hertz that our network has, is how many periods occur in the unit of time, which is the second. In other words, how many alternations does the second make? This is the frequency. The frequency is symbolized by F, like this, and it shows us how many times these occur, how many alternations in a second. This is the frequency. When we say that is in our network, that it is 50 hertz like this, it is how many times it makes alternations in a second, how many periods that is fit into the time in 1 second. We said 30 hertz, right? And in our network, we have 50 alternations per second. That's why we don't see, there we also mentioned the flickering lamp. Imagine, in 1 second, it does this thing 50 times. That's right. Period and frequency are not only characteristic of alternation, they are also present in pulses. Whatever is repeated as a point, that is, or whatever is repeated in general, and in a wave, in a lath, as the saying goes, if we have this repetition, we say that we have frequency and period. Now, with electronic pulse recorders, now we no longer need to count boxes. And to calculate how frequency and period are, it shows us directly electronically both the frequency and the period and everything. They have become simpler, that is now, compared to the analog oscilloscopes, where we needed to count squares and to adjust and to do. Now simply we place the probe on one of the oscilloscope's oscillators, and immediately we say its frequency. It is enough, of course, to understand the circuit, that is, that this is the oscillator, and we need to measure it with the oscilloscope to see what frequency it produces. So let's look at another simple little circuit like this to understand a bit the difference between voltage and current. Let's assume that I have a voltage source, say 5 volts. I will create a source and a resistor, the simplest circuit that can be made, and I know when this circuit closes that I will pass current through it. With the voltage of 5 volts that we provide, with a direction from the anode and intensity proportional to the voltage, and inversely proportional to the resistance we have put. So I understand that the voltage will remain stable at 5 volts, while the current will pass according to the resistance we will have put here. The current intensity, in other words, is not constant. If I have a 5-volt 10-amp battery, it implies that whatever circuit I create, I will pass through 10A. The 5 volts will be standard, but the 10A will be determined by the load provided. We will provide it to the battery. For example, if our load is the resistance, the smaller the resistance, the more 10A will pass through the circuit. As the resistance increases, the 10A decrease. This now in repairs, usually we do not measure the 10A. There is no need to measure. Usually we measure the volts passing through the circuits. And a characteristic when we see some designs is the grounding. In the drawing, grounding is usually present and symbolized as I do on the piece of paper. And there may be other circuits that are grounded and other circuit components, the capacitors, the penalty, which will be grounded. All this now implies all these ground connections. That is, it's like an egg, all connected together. This is understood in the plans when we read it, and there we usually also put the probe of our multimeter, or the grounding of the oscilloscope, and we start taking measurements with the positive or with the negative in the rest of the circuit to find some fault. Let's create another small circuit, the same with the voltages but a few more in parallel, to show you how we will measure if we had a board with our multimeter. So I will use 3 resistors. I will connect my source. I will connect with grounds. I will not connect everything together. So in this circuit, how do we see 3 resistors, 1 source? Let's assume our source is 10 volts. If we were to measure now if the source is 10 volts, and we measured the voltage across the resistors from end to end, like we measure with the multimeter, we would find on this resistor about 3 volts. In the next one, we would find 5 volts. When we measured the resistance like this with the multimeter, and in the other one, we would find 2 volts. So we see that the voltage is divided across the resistors, 3, 5, and 2V, and they add up to 10 volts, which is our source. But on the normal top plate, we will not sit to count the resistors one by one above when the current dissolves. We are not interested in doing this thing to take a resistor to measure its voltage, because it's the voltage drop. We're not interested in this, usually in repairs. How much voltage drop exists across a resistor? This has been calculated by your construction, and the rest of the circuit will essentially work because it has put resistances on you. We want to see if we have any interruption in our circuit thanks to resistances on them. If we have any interruption, so we will put our multimeter in the minus on the ground, which is over here on the board, and we will start with the positive to measure on the circuit to see what's going on. So if we had this circuit on a slope above, we would put the accept, we would put it on the descent, and we would measure with the sum. We would find here to see if we have a tendency, and what tendency we would have over there now like this. If we measured here, we would find that we have 10 volt minus 3 volt voltage transients, the first resistance. So if we measured here with a winding, we would measure here 7 volts. Like this over here, we would find 7V at this point. So we would understand that the resistance is correct. We would continue further down. At the next resistance we would measure over here, we will see that it would output 2V, so we will understand that this resistance is correct as well. And we would continue with our circuit up and down in the next resistance. Of course, we would find 0V because it's a short circuit, and even this indication, however, will have a meaning that there's continuity of the short circuit, whatever the 2 resistors together mean. And of course, visually, if we were looking at it now, we would see that the current is flowing through the resistors from plus to minus, so we have a flow of current whose intensity has been regulated by these resistors here. And not by the 10 volts of the source. So we said the current is regulated by the loads, which in this specific case are our resistors. And we said that in repairs we don't need to calculate the current. Someone else has calculated it for us. Let's not repeat it. So that's all for today. I hope I didn't confuse you too much. Of course, any questions, comments, you can write to me, explanations if you want me to tell you something else. I always talk about repairs. We don't do constructions over here. Don't let some people get upset again and say why we don't learn types, because we're not interested in currents and such. We always talk about repairs. If we want to do some construction, of course, we need types to calculate currents, to calculate resistances, to drive transistors, or various such circuits. I want us to imagine the current, how it flows through the various circuits. like that, to have an understanding of what happens when current flows through our circuits. Today we talked about hesitations. In another lesson, we will cover transistors, diodes, although I have made videos with rectifications and such that I have explained. And let us remember that repair is a matter of chance. Repair is not calculated. That's how it is. If we don't measure, we should specifically change components and not start changing until we find the burnt one. That is not called repair. Until the next video, have fun. Greetings to everyone.